Electric potential is a fundamental concept in electromagnetism. It represents the amount of work needed to move a unit positive charge from a reference point, usually infinity, to a specific point in an electric field. To understand this concept, imagine we have a positive source charge Q, creating an electric field around it. The dashed lines represent the electric field, pointing radially outward from the positive charge. Now, if we want to move a small positive test charge Q from far away toward the source charge, we must do work against the electric field. The charges repel each other, so external work is required to bring them closer together. Electric potential is measured in volts, where 1 volt equals 1 joule per coulomb. This tells us how much energy per unit charge is stored at that point. Importantly, electric potential is a scalar quantity, meaning it has magnitude but no direction. It's crucial to distinguish electric potential from electric potential energy. Electric potential is the work per unit charge and is a property of the electric field itself. Electric potential energy, on the other hand, is the total energy that a specific charge possesses due to its location, calculated as charge times potential. Understanding electric potential is fundamental to analyzing electric circuits, capacitors, and many other electrical phenomena. It provides a way to describe the electrical state of any point in space without needing to consider specific test charges. Understanding the difference between electric potential and electric potential energy is crucial in electrostatics. These two concepts are related but fundamentally different. Electric potential, denoted by V, is a property of the electric field itself. It exists at every point in space around a charge, regardless of whether we place a test charge there or not. Electric potential energy, denoted by U, depends on both the electric potential at a location and the magnitude of the charge we place there. It's the energy a charge possesses due to its position in an electric field. The relationship between these quantities is given by the equation U equals Q times V, where Q is the charge and V is the electric potential at that location. To better understand this distinction, let's use an analogy with gravitational potential energy. Think of electric potential as the height of a hill. It's a property of the terrain that exists whether or not we place anything there. Now, electric potential energy is like the gravitational potential energy of a ball placed at that height. A heavier ball at the same height has more gravitational potential energy, just as a larger charge at the same electric potential has more electric potential energy. Similarly, in electrostatics, the electric potential is like the height. It's the same at a given point regardless of what charge we place there. But the electric potential energy depends on both this potential and the magnitude of the charge, just like gravitational potential energy depends on both height and mass. The electric potential, due to a point charge, is given by a fundamental formula in electrostatics. This formula allows us to calculate the potential at any distance from a charged particle. Let's break down each variable in this formula. V represents the electric potential measured in volts. The constant K is Coulomb's constant, approximately 8.99 times 10 to the 9th power Newton meters squared per Coulomb squared. Q is the magnitude of the point charge in coulombs, and R is the distance from the charge in meters. An important aspect of this formula is the sign convention. The potential will be positive for positive charges and negative for negative charges. Now let's work through a specific example to see how this formula is applied in practice. Here's our example problem. Calculate the electric potential 1 meter away from a positive 1 microcoulomb charge. Here we have our positive charge, and we want to find the potential at point P, which is exactly 1 meter away from the charge. Now let's solve this step by step using our formula. Step 1. Let's identify our given values. We have Q equals positive 1 microcoulomb, which is 1 times 10 to the negative 6 coulombs. The distance R is 1 meter, and we use Coulomb's constant K equals 8.99 times 10 to the 9th power. Step 2. Now we substitute these values into our formula. Step 3. Let's perform the calculation. We multiply 8.99 times 10 to the 9th by 1 times 10 to the negative 6, then divide by 1. Therefore, The electric potential at a distance of 1 meter from a positive 1 microcoulomb charge is 8,990 volts. This positive value confirms that we're dealing with a positive charge, as expected from our sign convention. Electric potential is a scalar quantity, which means it has magnitude but no direction. This important property allows electric potential to follow the principle of superposition. The superposition principle states that the total electric potential at any point is simply the algebraic sum of the potentials due to each individual charge. Since potential is scalar, we add the values directly, paying careful attention to their signs. Let's demonstrate this with a concrete example. We have 2-point charges, a positive charge of +4 microcoulombs and a negative charge of -2 microcoulombs, separated by a distance of 6 meters. Now we want to find the total electric potential at point P, which is located 3 meters from the positive charge and 4 meters from the negative charge. First, let's calculate the potential due to the positive charge. Using the formula V equals kq over r, we get V1 equals 9 times 10 to the 9th times 4 times 10 to the -6th divided by 3, which equals 12,000 volts. Next, we calculate the potential due to the negative charge. V2 equals 9 times 10 to the 9th times -2 times 10 to the -6th divided by 4, which equals -4,500 volts. Notice the negative sign from the charge. Finally, we apply the superposition principle. The total potential at point P is the algebraic sum. V total equals V1 plus V2, which equals 12,000 volts plus -4,500 volts, giving us 7,500 volts. The key insight is that we must carefully consider the sign of each charge when adding potentials. Positive charges contribute positive potential, while negative charges contribute negative potential. The algebraic sum gives us the total potential at any point in space. Equipotential surfaces are fundamental concepts in electrostatics. These are surfaces where the electric potential has the same value at every point. The key property of equipotential surfaces is that no work is required to move a charge along these surfaces since the potential difference is zero. Let's examine 2 important examples. First, consider a positive point charge. The equipotential lines around it form concentric circles with higher potential closer to the charge. Electric field lines radiate outward from the point charge and are always perpendicular to the equipotential circles. This perpendicular relationship is fundamental. Our second example shows parallel plates with opposite charges. Here, the equipotential lines are straight and parallel to the plates, while the electric field is uniform and perpendicular. The electric field between parallel plates is uniform and points from positive to negative. Notice how the field lines are perpendicular to the equipotential lines. Now let's demonstrate the key principle. Watch as we move a charge along an equipotential line. Since the potential is constant, no work is done regardless of the path taken. Remember the fundamental relationship. Electric field lines are always perpendicular to equipotential surfaces. This perpendicular relationship ensures that moving along an equipotential surface requires no work. To better understand electric potential, we can draw a powerful analogy with gravitational potential, which is simply the height of an object above a reference point. Imagine a hill with varying heights. Objects naturally tend to roll downhill, moving from areas of higher gravitational potential to lower gravitational potential. Watch as this ball demonstrates the natural tendency to move toward lower potential energy. It rolls downhill, converting potential energy to kinetic energy. Now let's see how this gravitational analogy applies to electric potential and the behavior of electric charges. In electric potential, positive charges behave like the ball on our hill. They naturally move from high electric potential to low electric potential. A positive charge moves naturally from high potential to low potential, just like our ball rolling downhill. However, negative charges behave oppositely. They move from low potential to high potential, like a ball that would roll uphill if gravity were reversed. This fundamental principle explains how voltage works in electrical circuits. Voltage is simply a difference in electric potential. In this circuit, the battery creates a voltage difference, a potential difference between its positive and negative terminals. This potential difference drives electric current through the circuit. Charges flow from high potential to low potential, just like water flowing downhill or our ball rolling down the slope. The gravitational analogy helps us understand that electric potential differences create the driving force for electric current, making it possible for electrical devices to function. To better understand electric potential, we can use the familiar analogy of water pressure in a plumbing system. This comparison helps us visualize how electric potential works in circuits. In a water system, we have tanks at different heights, creating different water pressures. The higher tank has greater pressure, while the lower tank has less pressure. When we connect these tanks with a pipe, water flows from the high pressure area to the low pressure area. This pressure difference drives the water flow through the system. Similarly, in an electrical system, we have regions of different electric potential. High potential regions are like high pressure areas, and low potential regions are like low pressure areas. Electric charges flow from high potential to low potential, just like water flows from high pressure to low pressure. The electric field lines show the path that charges would follow. Let's now directly compare these two systems to see the key analogies that help us understand electric potential. Here are the key analogies. Water pressure corresponds to electric potential. Water flow corresponds to electric current. A pressure difference drives water flow, just as a voltage difference drives electric current. Finally, just as a water pump creates pressure difference to drive water flow, a battery creates voltage difference to drive electric current through a circuit. This water pressure analogy provides an intuitive way to understand electric potential and how it drives the flow of electric charge in circuits. Electric potential has numerous practical applications that power our modern world. Understanding these applications helps us appreciate how fundamental physics concepts translate into everyday technology. Batteries are one of the most common applications of electric potential. Inside a battery, chemical reactions create a separation of charge, establishing a potential difference between the positive and negative terminals. Capacitors store electrical energy by maintaining a potential difference between two conducting plates. When charged, one plate accumulates positive charge while the other accumulates negative charge, creating an electric field between them. In electronic circuits, different voltage levels control the operation of various devices. Transistors, microprocessors, and other components rely on specific potential differences to function correctly and process information. Understanding electric potential is fundamental to comprehending electromagnetism and electronics. From the batteries that power our devices to the circuits that process information, electric potential is the driving force behind modern technology. This knowledge forms the foundation for advanced studies in physics and engineering.